Hello, everyone. My name is Josh. I'm a second-year materials student at the University of McMaster, and today we're going to be going over the standard state in the thermodynamics of mixing. More specifically, mixing of different solutions. Now, let's start off by just recalling what is a standard state. Well, a standard state is what we measure the Gibbs free energy to be at zero. Our standard state, we're choosing for some phase to be at zero while we go and we try to develop our mixture. Now, let's start very, very simple. I want you to just take whatever you know about this standard state stuff, and if you don't understand it at all, that's even better. I just want you to forget it, and I want you to try to listen to my explanation of this, because I believe that this is a pretty good explanation of how this stuff works. So we're going to say our standard states are determined by melting points. We can choose different standard states at different parts of our mixture, at different temperatures. So we can have different standard states at different temperatures. Now, we're going to start with some very easy examples here. Starting with if our temperature is all the way up here at this green line. What would we choose our standard state to be? Well, we can see we're well above the melting point of A, and we are slightly above the melting point of B, which means we have all liquid. So if we have all liquid, a good point would be to say we're going to make our standard state of A be a liquid and B also be a liquid. Since when we have all A, we have a liquid, and when we have all B, we have a liquid. Now, let's go down here to this blue line. Now, we have all solid. Let's try to find standard states for this, for A and for B. Let's start at B. If we have all B, well, we have a solid. If we go over and we have all A, well, we also have a solid. What gets a little bit tricky is when our T is at this purple line over here. Now, look at either end. Our A goes ahead and it starts as a solid or a liquid, but our B over here, that's a liquid. So you might be asking yourself, all confused, how am I going to choose my standard states here? How am I going to know when the Gibbs free energy is zero for either one? Now, let's draw a Gibbs free energy curve. All right, so I've set up this Gibbs free energy curve here. And now, let's try to analyze and see what's going to happen if we choose both of the parts of our mixture to be at the same standard state. So let's say in this curve, I want my standard state for A and my standard state for B to both be liquid. What's going to happen? Well, if I have all A, and let me set up the axes of this chart, and we are working at the purple temperature. For all these graphs, we're going to be working at that purple temperature. So I know if I have all A, I'm going to have a liquid. So that's fine. From there, I'm going to draw my normal Gibbs free energy curve just like that. Oops. I'm going to draw what it would normally look like. Can I get a parabola, please? Thank you. Now, I have some minimum point, and then I'm going to start increasing again. Now, I know right here, this is my standard state of A, and it is a liquid. So I know A is a liquid, so it's going to be at 0. But what is B? It's not a liquid, so I can't bring this to 0, can I? No, it's not a liquid. So what do I know about these Gibbs free energies? Well, I know that my Gibbs free energy for B is going to be 0 when its standard state is a solid, because my Gibbs free energy of B wants to be a solid at this temperature. So let's say the Gibbs free energy of B, if its standard state was a solid, is 0. Now, what's going to happen if it's a liquid? Well, does my B, does that want to be a liquid? No. So what am I going to have to do if it's a solid? I'm going to have to add some energy to it. I'm going to have to try to melt it maybe. So its Gibbs free energy, if its standard state is a liquid, is going to be up here. This is what it looks like if it wants to be a liquid. Now, what is the difference in this value, you might ask? What is this value? Well, it's going to correspond to the change, the Gibbs free energy at a liquid minus the Gibbs free energy at a solid. What does that correspond to? Well, that's just the Gibbs free energy due to melting. And that's going to be equal to the enthalpy of melting minus T times the change in entropy of melting. If we assume our enthalpy of melting is equal to our entropy of melting, or sorry, not equal, not those two. Sorry about that. We're going to assume our specific heat capacity of our solid is equal to the specific heat capacity of our liquid, which allows us to use this as our Gibbs free energy of melting equation. Just like that. Oops, I misplaced my T's. We have our melting minus whatever temperature we're at over our melting. So this will give us, it will yield a positive value. Okay, let's now do the same thing, but we're going to say both are at a solid standard state now. All right, so I've set up my Gibbs free energy chart here. Now let's say we want to start with our Gibbs free energy of our standard state of B being a liquid. Sorry, being now a solid. Well, that works fine because we know at this temperature, B is a solid. So its Gibbs free energy is going to decrease. Let's see if I can get that parabola going again. I'll just try it one more time. Maybe one more. There we go. Okay, my Gibbs free energy is going to decrease. But what's my A at this temperature? Well, my A is a liquid. So the Gibbs free energy is going to be 0 when my standard state is a liquid. What does this mean? Well, I'm going to have to add some energy to make it a solid. The Gibbs free energy, standard state for A as a solid, is up there. Now, what is this difference now? Well, that's going to correspond to now the negative change in Gibbs free energy due to melting, or the Gibbs free energy we need to freeze it. And that's going to be equal to the same thing. Enthalpy there for A times the temperature of melting for A minus T divided by the temperature of melting for A. Perfect. Now look what I've done here. What I'm doing is I'm going to split up my graph into different regions, and I now have a couple different Gibbs free energy curves. I'll just do this actually for now. So I have my Gibbs free energy curve if I were to choose liquid to be my solid state for both, and I have it where I were to choose solid to be the solid state. Now look here, I can draw my common tangent just like anything else. This splits up my regions now. And it looks just like how it does in the graph. First, my liquid region is going to be the one that is has the lowest Gibbs free energy, so it's stable. And then the two are stable at the same time, and then the solid is stable. If I were to repeat this for different standard states, I would find that standard state does not dictate where equilibrium is. What I mean by this is if I were to do this and I were to change the standard states of each, wherever equilibrium is going to be within the same composition. On all my different composition charts, or all my different Gibbs free energy charts, sorry, the composition in which I have a stable state or stable phase with two coexisting phases are always going to be within this rectangle that I've just drawn out. That's something really important that you're going to have to remember. Now, let's talk about activity. So since we know this here stands for the Gibbs free energy of melting. Since we know the Gibbs free energy of melting is greater than 0, and it corresponds to the activity of B as a solid divided by the activity of B as a liquid, and this is going to yield us positive. So we know the activity of B as a solid is greater than the activity of B as a liquid. Now what we can do with this information is make different activity plots with different standard states of B. Now for this first activity plot, we're saying this is activity, and this is mole fraction. We know that our B is going to start at 1 for the activity. Standard state to be solid. When we have all of B as a solid, the activity of all of our B is going to be 1 along with when we have all B for our mole fraction. We know it's going to exhibit ideal behavior up until it reaches a certain point. At this special point, our solution is going to undergo a phase transformation. And our activity, we know, has to be constant under a phase transformation. From here, we have to get back down all the way down to 1 because we know when we have no B, the activity of B is 0. Now let's do the same thing if we were to have our standard state be liquid. So we know that if our standard state is liquid, we're going to start all the way down here now. And if we were to start as a liquid, we would go under ideal conditions. From here, we're going through a phase transformation. Now, what I cannot do is this, is I can't bring my activity to 1 where my composition is 1. Why is this? Well, I know my activity when I'm a liquid is less than the activity as a solid. And I just said when I have all solid be at all of our activity is 1. So this is going to have to be less. When I merge these two graphs together, you'll see that this turns out, this makes sense. With all of that being said, hopefully everything in this video made sense to you. In the next video, we're going to be going over examples of drawing Gibbs free energy and activity curves on phase diagrams. Thanks.